Have you ever looked up at the night sky and wondered, are we alone? From life that thrives in boiling vents deep under our oceans to mysterious radio blips from the stars, the search for life beyond Earth has moved from myth into serious science. Today we'll trace that search, the evidence we have, the experiments underway, and the hard questions that still divide scientists. Why does it matter whether life exists elsewhere? The question echoes through centuries of human inquiry, because finding life, even the simplest microbe, would be the most profound discovery in history. It would force a complete rewrite of our textbooks on biology and chemistry. For the first time, we would have a second genesis to compare with our own. Is life always carbon-based? Does it always require liquid water? Is DNA the only way to pass down genetic information? This discovery would represent the final step in the Copernican revolution. Not only is our planet not the center of the universe, but our very biology might not be special. It would be the ultimate confirmation that we are not a miracle, but a natural, perhaps even common outcome of cosmic evolution. Suddenly, we could begin to distinguish which features of life are universal principles and which are merely quirky accidents of Earth's specific history. Are two eyes a common solution for sight? Is intelligence an inevitable outcome of complexity? The implications would ripple through every facet of human culture, challenging long-held beliefs in philosophy and religion, and fundamentally redefining our place in the cosmic narrative. The stakes of exploration would skyrocket, transforming it from a quest for knowledge into a search for kinship. To find where life might be, we first had to look at the most unlikely places on Earth. We once thought life required gentle, sunlit ponds, but our planet proved us wrong. We discovered the Extremophiles, organisms that don't just survive in hostile environments, they thrive. In boiling, acidic hot springs, microbes flourish in waters that would dissolve metal. At the bottom of the ocean, in eternal darkness and under immense pressure, entire ecosystems cluster around searing hydrothermal vents. They don't use sunlight, they perform chemosynthesis, feeding on chemicals from the Earth's core. Deep beneath the Antarctic ice sheet, in lakes isolated for millions of years, life persists in the freezing dark. And miles below our feet, a deep biosphere of microbes lives within solid rock, metabolizing at a glacial pace. These tenacious organisms completely redefined habitable. They are our blueprint for where to look next. When we see the rusty plains of Mars, we now think of rock dwellers and wonder if Martian life simply went underground. When we look at Jupiter's moon Europa or Saturn's Enceladus, with their hidden global oceans, we imagine their dark seafloors, potentially warmed by hydrothermal vents identical to our own. These extremophiles even give us permission to consider the truly bizarre. Could acid-loving microbes float in the temperate upper layers of Venus's sulfuric acid clouds? Could life on Saturn's moon Titan exist not in water, but in lakes of liquid methane? The lessons from Earth's toughest life have transformed our solar system from a collection of barren rocks into a gallery of tantalizing possibilities. The search for life begins not with biology, but with chemistry, a cosmic chemistry that unfolds across the vastness of space. For decades, we viewed space as a sterile vacuum, but our most powerful telescopes have revealed a universe teeming with organic chemistry. In the cold, dark hearts of interstellar clouds, where new stars and planets are born, astronomers detect the faint signatures of complex molecules. Using radio telescopes like ALMA, they identify the spectral fingerprints of carbon-based compounds. We've found them hitching rides on comets, as the Rosetta mission discovered on Comet 67P, and dusted across the protoplanetary disks that will one day coalesce into new worlds. These aren't just simple compounds. We've identified glycine, the simplest amino acid, glycolaldehyde, a basic sugar, and vast webs of carbon chains. These are the fundamental building blocks of life as we know it. Their presence across the galaxy strongly suggests that the raw ingredients for life are not rare, but universal. This is the great unknown, the transition from complex, non-living chemistry to the first spark of biology. On Earth, this process of abiogenesis remains one of science's most profound mysteries. Did life arise in hydrothermal vents or warm little ponds? We may never know for sure, but by studying the chemical inventory of the cosmos, we understand that whatever process occurred here could, in principle, occur elsewhere. And now, we know exactly where to look. Until the 1990s, planets beyond our solar system were merely theoretical. The groundbreaking discovery of 51 Pegasi b in 1995, a hot Jupiter orbiting a sun-like star, opened the floodgates. In the decades since, our catalog has exploded. Missions like NASA's Kepler and TESS, using the transit method to detect the faint dimming of a star as a planet passes in front, have confirmed over 5,000 exoplanets. Statistically, this means our galaxy likely hosts billions of worlds. Many of these newfound worlds orbit within their star's habitable zone, the temperate region where liquid water could potentially exist. We've discovered a surprising diversity: rocky super-Earths, gaseous mini-Neptunes, and worlds orbiting dim red dwarf stars. But the true frontier is analyzing their atmospheres. With the power of the James Webb Space Telescope, we are beginning to decipher the chemical makeup of these distant skies, searching for biosignatures, gases like oxygen and methane, that could indicate a living, breathing biosphere. Each new discovery brings us one step closer to answering the ultimate question: are we alone? What would count as life from light years away? Scientists look for biosignatures, atmospheric gases out of chemical balance, surface pigments, or seasonal changes. But false positives are real. Geology can mimic biology. Detecting a robust biosignature means ruling out non-biological explanations. For decades, projects like SETI have listened for deliberate or accidental radio signals. The famous 1977 WOW signal remains unexplained, tantalizing but not repeatable. Modern searches use big sky surveys, narrowband radio detectors, and optical lasers. The search is now faster and more automated than ever. Moons like Europa and Enceladus hide oceans beneath ice. Cassini flew through plumes on Enceladus and found organic molecules. Europa Clipper and future missions aim to sample plumes or map subsurface oceans. If energy and chemistry are present, microbial ecosystems could exist in these hidden seas. Mars once had rivers, lakes, and a thicker atmosphere. Rovers now find ancient lake beds, organic molecules, and seasonal methane spikes. None are definitive proof of life, but Mars remains our closest laboratory for testing whether life emerges easily on wet worlds. The Drake equation frames the question of how many civilizations might be detectable. Each factor, star formation rates, fraction of habitable planets, fraction that develop life, fraction that become detectable, carries massive uncertainty. New exoplanet data helps narrow the first terms, but the emergence and longevity of life are still wide-open questions. If life is common, why haven't we seen it? Possible answers range from rare life or intelligence to short-lived technological phases to deliberate silence by other civilizations. Perhaps interstellar colonization is harder than we imagine, or perhaps signals are unrecognizable. Fermi's paradox pushes us to refine hypotheses and search strategies. The coming decade will be decisive. Our new generation of eyes on the sky, like the James Webb Space Telescope and ground-based extremely large telescopes, are dissecting the light passing through exoplanet atmospheres. They hunt for chemical fingerprints of life, combinations of gases like oxygen and methane that suggest a biological source. Meanwhile, missions like the Europa Clipper and Dragonfly are taking the search directly to our solar system's most promising moons. Clipper will use radar to map Europa's hidden ocean and taste its plumes, while Dragonfly, a nuclear-powered quadcopter, will analyze the organic-rich dunes of Titan, searching for the chemical precursors to life itself. The search for intelligent life is also entering a new era. The hunt for radio signals is being supercharged by instruments like the Future Square Kilometer Array. But we're also expanding our methods, with optical SETI projects scanning for powerful pulsed laser signals. At the same time, our understanding of what to look for is getting sharper. In laboratories, scientists are recreating the primordial soups of alien worlds. By simulating the atmospheres of early Earth or Mars, they map the pathways from simple chemistry to the building blocks of life. This crucial work helps us distinguish a true biosignature from a geological quirk, ensuring that when we find a signal, we can be confident in what it means. But finding an answer will change everything. The discovery of even a single microbe on Mars would prove that life is not a unique miracle of Earth. It would force us to confront immense ethical challenges. How do we explore these new ecosystems without contaminating them, a concept known as forward contamination? And what are the risks of bringing an extraterrestrial organism back to our own biosphere? The implications of detecting an intelligent signal are even more staggering. It would instantly reshape our understanding of our place in the universe, impacting every facet of human culture, from philosophy to religion. It forces us to ask, are we ready for the answer? Because of these high stakes, preparing for discovery is as important as the search itself. Scientists are actively developing frameworks for this eventuality. Post-detection protocols outline the rigorous steps needed to verify a signal and call for international consultation before any public announcement. The most debated part is whether we should reply. This preparation requires more than just rules. It demands scientific humility. We must be ready for life to be utterly alien, to defy our carbon-based, DNA-centric expectations. The universe is under no obligation to conform to our imagination. Ultimately, this grand endeavor is a mirror held up to ourselves. Whether we find that the cosmos is teeming with life, or that we are utterly alone, the result will be equally profound. A silent universe would underscore the immense preciousness of our own world. A living one would open a new chapter in the human story. Either way, the search itself is one of humanity's greatest adventures, pushing us to the very limits of our curiosity and ingenuity. The journey is far from over. What do you think is the greater challenge? The technical difficulty of finding life, or the societal challenge of dealing with the discovery? Share your thoughts in the comments below, and subscribe for more deep dives into the universe's biggest questions.